Okay, maybe let's get started. We are very happy to have Gautam joining us as a postdoc at the Gravity Initiative. He finished his PhD at Chicago University. Today he will talk about why black holes are watching us.
Okay, thanks for the introduction. Thanks for accommodating me in the schedule. I know my travel plans were not ideal. I'm still really jet lagged, I should say. So, that's why I only have 10 slides. I'm going to take things pretty slow. So this so I don't have a pointer, but let me just do this. So this is an essay that I wrote with Bob Wall and Dane Danielson, who's a graduate student at Chicago. And so so what I'll describe today is the essay. There's an upcoming paper that is much more detailed that will come out that generalizes what I'll talk about today to all horizons. But today I'll just explain the simple case of the black hole horizon and why it's watching you. This is all the techniques are actually based on an earlier paper that I'll allude to a couple times in this talk by Bob, Dane, and I as well, that came out shortly before the essay. Let's advance my slides. Okay, so this slide is meant to frame the discussion that I'll be kind of talking about today. Well, the discussion largely, at least by the end of the talk, will be about quantum gravity. And as you all know, and hopefully are aware, quantum gravity is currently discussed, debated. What are the fundamental principles, properties of quantum gravity, even to this day? And it's really interesting to go back and read about how people way back when in the 50s or the 60s really thought about quantum gravity. And this Chapel Hill conference was the topic of quantum gravity was widely discussed. You can actually read the whole transcript from these discussions between Wheeler and Feynman and DeWitt and others. And many people were proposing many kind of bottom-up approaches to quantum gravity, where you postulate various principles or fundamental building blocks, and then you try to infer something from these building blocks. Feynman, in a kind of characteristic style, took a completely opposite approach to the question. He really said, well, I don't know what the building blocks of quantum gravity are, but it might be nice or interesting to probe properties of quantum gravity. And it's useful to do so to consider situations where we understand quantum theory, but also gravity plays an essential role. So one very simple example of this is if I take a massive body and then just put it in a spatial superposition of two spatially separated states, this body sources some gravitational field, and there's no way to describe what's going on here without invoking some aspects of quantum gravity. Right? I have a gravitational field and a superposition, but just by this statement. I see almost a question, but I guess I'll wait to. Okay, so sure. Okay, so that's what he suggested. We should start considering those kinds of things just to get started, and maybe we can probe aspects of quantum gravity from even this low level. And actually, the paper the bottom paper here was really a question of what can we learn about such such low energy superpositions of massive bodies. These are, Feynman posed this as a Gedanken experiment. It's now an actual experiment that will be done fairly soon, and so it's of interest to understand what can you learn from this. What I'll be talking about today, you should really think of as a Gedanken experiment. Maybe in 2 centuries or so, we'll be able to get to a point where we can do the experiment, but this is not a proposal. It's more of really in the spirit of Feynman. We shall show that such a Gedanken experiment, like the ones Feynman was discussing, provide insights into the relationship between black holes and decoherence in a quantum theory of gravity. Okay, so that's just the high level discussion of the talk. And let's continue the high level for one more slide before we get into all the details. So black holes and decoherence. I tend to walk around. I hope the Zoom yeah, I guess they can see me. Black holes and decoherence are two things that, do naturally come together. You should already kind of think of black holes as they're very well-known destroyers of quantum coherence. There are very trivial examples. Like if I take an entangled pair of particles and I just throw one member into the black hole, well, the member that I've kept outside the black hole for all observers outside the black hole will be completely decoherent. It will be in a mixed state because I threw the other one all the way into the black hole. There's even, much more. If we're starting to throw things into black holes, we could have taken a star, it's in a pure state, it collapsed and formed a black hole. I could start throwing other pure boxes of matter into this black hole. And we know that, eventually over a very, if you have a solar mass black hole, this will take some time, but eventually the black hole will emit Hawking radiation. And at least, up to a page time at the very least, this radiation is mixed. So this black hole is spewing out this mixed radiation, and whether or not it continues to do so or does so after a page time has no bearing in this talk. There's absolutely nothing related to it. But all I'm saying is that you should already think of black holes in some sense as engines of decoherence. Okay? But what I'm going to explain is that black holes are kind of even more insidious destroyers of quantum coherence than you might have already thought. Okay, and just to give away the punchline of this talk, the main result is that if you take any quantum matter and put it in a spatial superposition outside of a black hole, the black hole, in the vicinity of a black hole, the superposition, the coherence of the quantum superposition will be destroyed in finite time. Okay. So what is the picture? So this is again a cartoon. We'll do all precise diagrams later. This is the black hole. I took a particle, some massive body. I put it in a spatial superposition. So this is what this shaded object guy is. It's the, I put it in a spatial superposition of two spatially separated states. And I'm saying that if you just hold it there, after a finite amount of time, these superpositions will no longer interfere with themselves. Go ahead.
Even if I move them infinitely far away.
Infinitely far away, the effect is, it just takes, so infinitely far away, no. If you take the farther away you are, the effect takes longer.
How does it scale?
Well, I'll get exact formulas for you. Okay, well, I'll send you a paper. Okay. Okay, so let me just give, since I'm in the mode of giving away all the punchlines, the black hole acquires this which path information on the quantum superposition via the long range fields sourced by the superposition. And by the fact that these long range fields register on the horizon of the black hole then inflicts a fundamental rate of decoherence of any quantum superposition held in its exterior. That's the punchline. So what I forgot to put in my diagram are exactly these long range fields. Okay, and these are going to register on the horizon of the black hole, and I will explain to you exactly how the black hole, in this sense, watches this superposition. Okay. So now let's get out of the high level stuff and do a calculation. So to make this a precise experimental question, we'll have an experimenter, Alice, as usual. In this case, there'll be no Bobs, unless you think of the black hole as Bob. But there'll just be an Alice. She's going to create a spatial superposition and then check for its quantum coherence. And I'm going to go explicitly through the exact protocol that Alice is going to go through. Okay. Okay, so before we go to the black hole space-time, let's just do the simple protocol in flat space-time, where we should also see why decoherence. Well, Alice Well, she has a particle. So this is not an elementary particle. What I'm thinking of is a nanoparticle or some, atom or something. She has some particle. This is just, I just want, it's just to make the Gedanken experiment simple. I just want, the only real degree of freedom to be its center of mass. And it's going to have spin. Okay. And she's going to pass it through a Stern-Gerlach apparatus. So she could do lots of different, experimental colleagues of mine have now told me this is an old way of making superpositions. There's much more fancier methods they have with lasers and stuff like that. But you can do whatever you want. But I want you to create a 50-50 coherent spatial superposition of this particle. And this spatial superposition, the distance between the center of mass is going to be of size d. Okay, and so just to get you in the mood of thinking about spatial superpositions, this is the wave function of the particle that I want you to consider. It's spin up and to the left with wave function of Alice's particle to the left, and plus spin down and to the right with wave function of Alice's particle to the right. So the A's correspond to the wave function of the particle. Okay. So and let's just do the electromagnetic case, where the particle has charge. We'll do the gravitational case at the very end, but it's just simpler to think about the electromagnetic case. Okay. So what is she going to do? This is a very simple protocol, but obviously technically, maybe difficult to do in the lab, but again, this is a Gedanken experiment. She's going to maintain this spatial superposition for a time capital T, okay, in her lab. And then she's going to recombine by putting it through a reversing Stern-Gerlach apparatus. And she's going to recombine the superposition back together over a time scale tau. Okay. And there'll be a space-time diagram in a second as well. And then she's going to measure the coherence of her particle. How would she measure it? Well, in this particular example, her particle started in a coherent spatial superposition of spin up and down, let's say in the z direction, which means it has a definite up in the x direction, value. If it's lost coherence, then she could measure the spin in the x direction, and if she's completely decohered, half the time she will measure spin down in the x direction. Okay. So that's how she would check if she lost coherence. She would repeat this experiment the same way many times, and she would build up statistics. If she ever sees spin down in the x direction, she knows she's decohered to some degree, and she could measure how much. Okay. Okay, so this is the protocol, Alice. So this is a space-time diagram. So this, I'm glad I'm talking to a gravity group. I can just draw Penrose diagrams, and no one's too upset, hopefully. So so this is Alice's particle, and she's creating this spatial superposition. I'm assuming she's doing this very slowly at early times. She holds the spatial superposition over a time capital T, and then she's going to recombine the particle back together over a time scale tau, and then she measures the coherence of her particle at any time after that. Okay, by measuring the spin in the x direction. Okay. So why am I worried? Why am I worried about Alice's experiment? Well, Alice, in the absence of any other interfering effects, possible interfering effects were considered in my previous paper with Bob and Dane, but in this particular example where there's no absence of any other observers coming around, the only thing that can decohere Alice is any electromagnetic radiation that she might emit throughout this whole process, right? I neglected to include any electromagnetic effects in my whole discussion, and that's the only thing that is going to possibly decohere her. When their superposition is static, there is absolutely no radiation being emitted at all, but she might radiate which path information over the time she's accelerating the branches of her wave function back together, okay? So this is when she's recombining her particle. So what you might be worried about is the following, where if she's recombining her particle over a time scale tau, she might radiate, if she does this very quickly, she might radiate some which path information. And what does that mean? Well, if I look at the state asymptotically, which is the nicest place to think about radiation, Alice's particle might be tensored in with an electromagnetic state of Alice's radiation, going to the right along path 1, or Alice's radiation for along path 2. And all I'm saying is that if the radiation along path 1 is sufficiently different than the radiation along path 2, if she emits any which path information, then she should lose quantum coherence. Okay. And you can quantify this. I mean, so this is just, saying the same thing again. The decoherence is determined by the orthogonality of the radiation states that she emits. So this decoherence, if it's 0, that means that she's emitted, the radiation states are very, very nearly identical to each other, or exactly identical to each other in Hilbert space. Or if she radiates which path information, then that means that these states of Alice correlated with Alice's particle are, orthogonal to each other. Okay. And for this particular case, which is the simplifying case that I'm considering to make my life easier, when Alice has a particle, which means that these radiation states should be thought of as coherent states of the electromagnetic field, there's a really nice formula for this decoherence. This inner product, I hope it's not too small, this inner product can be expressed in terms of the number of what we call entangling photons, basically the expected number of photons in the difference of the two radiation states. So if Alice emits basically an order 1 number of entangling photons during the recombination process, then this exponential of order 1 means that she's going to be basically completely decoherent. Okay, so that's the intuition. If she emits an order 1 number of entangling photons, I hope you guys can see order 1 number of entangling photons, then she will be completely decoherent. Okay, very good. Okay, so again, why should you not be worried about this? Well, it's not hard to see that Alice, if she does this process incredibly slowly, she should ensure that she's not able to, she's not going to emit much or any which path information. And it's not hard to estimate how slowly you need to do this. If you recombine the particle over a time scale, there's an effective dipole that's being created here. It's not an actual dipole, it's just a single particle, but an effective dipole which sets a time scale of Alice's recombination. If the time scale of her recombination is much bigger than that, effective dipole time scale of Q times the separation, then she's not going to emit a lot of which path information, and the radiation states are going to be nearly the vacuum. Okay, so that's the statement that she's got to recombine very slowly, and the decoherence is, completely negligible. So you shouldn't be worried about this in flat space-time. There's no intrinsic rate of decoherence. Go ahead.
Is it correct to say that if I see decoherence, then I'm measuring an effect which has to do with quantization of the electromagnetic?
That was the subject of that bottom paper. Yeah, so that's a very good question. And the answer is yes, but it's non-trivial to argue that. And the analogous statement in gravity is a really important statement, a powerful statement. So we argued that but it takes a bit of work. It's not an immediate consequence.
But a classical actually.
Yes, but in order to really nail down all the details in that, it takes a little bit of work. But yes, it's a logical conclusion. That's a good question. Okay, so now let's do this outside of a black hole, and immediately we have a few more complications. So we're going to consider the analogous experiment outside a black hole. So first of all, I don't want Alice falling into the black hole. So her lab is going to have to stay outside the black hole. And I don't want her to emit any unnecessary radiation. So I don't want her falling even into the black hole, like, radially inwards. I'm going to keep her accelerating at some fixed position outside the black hole. Okay? Some fixed radius distance away from the black hole. And also, if she just, if her particle is freely falling in her lab, it's also going to fall towards the black hole and radiate. I'm going to need to apply some force to the particle to ensure that it follows a stationary trajectory. Okay, so I'm going to, for the electromagnetic case, let's apply some local electromagnetic field to ensure that it maintains some stationary trajectory. And so this is the diagram that you should think of. It's not the same as, I guess, what you see in Interstellar, but the key, this is all the features that I want. So this is a black hole. It's formed from gravitational collapse. That's not essential for nearly most of this talk, except for the very end when we talk about vacuum states. But it's formed from gravitational collapse. That's a singularity. That's meant to remind you that this is a black hole. That plays no role in this talk whatsoever. Alice is maintaining some fixed proper distance away from the black hole. She is ensuring that her particle, even the beams of her particle going to the left and to the right, are maintaining as close to stationary trajectories of the outside the black hole, so that she's trying to minimize as much radiation as possible in this whole process. And she's going to, in proper time of her lab, maintain this coherent, this spatial superposition for some time, capital T. And then she's going to recombine in proper time tau in her lab, the beams of her particle. Okay.
When you say minimize radiation, you mean electromagnetic?
At this point, yes, yeah.
The act of applying a force to be the station that doesn't be prohibited?
No, decoherence would be a statement of are you losing which path information? So by applying a force to the beams of the particle. Oh, you're saying not exactly so she can apply an electromagnetic field to maintain stationary trajectories, like an inhomogeneous electromagnetic field, which just forces the particles to go on stationary trajectories, but that will not cause them to emit any radiation at all.
But that field will interact with the particle.
Yeah. No. Why would you say that?
That's like a measurement. The stationary, the force that's keeping them when we measure them.
Yeah, so it's as long as you can increase the potential and then set it back to zero at the end, then there isn't any measurement of the positions of the particle. Like she can just turn the potential on and then turn it off without, that potential can exist and be created and destroyed without even particles even being there in the first place, right? So it's not a statement about if the particles are there or not. It's just a statement about turning on a potential and turning it off.
Potential has to be different for each time.
Yeah. So you can turn on, so the statement is that in Alice's lab, you can turn on a potential and turn it off. But the statement of if the particle is there or not is different than a statement of is there a potential there or not.
But I'm saying the potential to hold the particle which goes the right way on that trajectory is different.
Yeah. So I'm saying there is a whole potential with two wells, for example. Yeah. Yes, exactly. Yeah. So you could that would be the case where you would need to maintain these trajectories. But the statement that the potential exists is not a statement of where the particle went. Right. Okay. Good.
It's a statement that the particle couldn't have gone somewhere else.
Yes, that's true. But that's not, yes, that's true.
Is it necessarily needed? So to stay fixed in a location, say if you send the two entangled particle on a stable circular orbit or something.
Yeah, so if you did that, then the particles would start to radiate, and that would not be an optimal process. They would literally radiate out the sky. So I want to, ultimately I will want to minimize all radiation to sky. And this is the trajectories that would do that. Okay. Good questions. Okay, so the only difference between, besides all these other differences, the only difference between this protocol and the other one is that now radiation can propagate not only to null infinity, but also into the black hole. So I need to add more radiation states for the black hole, which I'll call these capital phis. Okay. And as before, Alice can minimize her radiation out to scry, as I was explaining earlier, by following these nearly stationary trajectories and quasi-statically recombining her particle. Okay, but now we will show that her particle must radiate which path information into the black hole. It is an unavoidable occurrence. And so let me just give you a couple more statements here. So now it's being covered, but the time scale needs to be bigger than this dipole's time scale, but there's also a time scale for just moving through this gravitational potential, that's set up by the black hole. So it's got to be bigger than, the time scale of m, basically, to avoid emitting radiation out to sky. I did something. Okay. I think it's what happens when I get closer. Yeah, yeah, there must be a black. Which one of you is a black hole? Okay, so I'm minimizing my radiation out to sky, but what I'm going to prove now is that you cannot minimize this, and it has nothing to do with this time scale and everything to do with this capital T. Okay. Okay, so let's go to a kind of different diagram so I can start setting up coordinates and whatever. So this is, again, Alice's experiment. She's slowly creating this particle. She's holding it for some amount of time, capital T, and then she's going to recombine and check for quantum coherence just as before. This is the black hole. And, so I probably don't need to review too much. I should not step on this cord. So the black hole horizon, this is time is going in this direction and space is in this direction. This is not the Penrose diagram from before. The light cones are now tipping over in the usual way. These cross sections of the black hole are spheres with metric Q, and these capital indices are going to be my sphere indices for this talk. V is the time along the black hole. It's very often referred to as affine time. It's just the choice of time that I'm using. It's related to the proper time in Alice's lab by this exponential here, which you could think of somewhat as a time dilation type factor between time on the horizon and time in Alice's lab. But this is the formula. And the what else do I need to say? Oh, and the radius r is basically this proper distance off the horizon of the black hole. Okay. So that's all I need for the setup. How much time is this talk? Do I have like half? Oh, okay. 1 hour. Oh, okay. Okay, great. I can go slower. Okay, are there any questions about the geometry? All right, we're good. Okay, so we're now in this slide, let's just completely forget about the Gedanken experiment and just do a warm-up problem just to see what's going on. And let's consider the simple warm-up problem of the radiation produced by the following object. So I'm going to take a particle, I'm going to hold it at some position outside the black hole, let's call it B, and then it's displaced to a new position over some amount of time to some new position, r equals B plus D, where I'm going to assume that my distance away from the black hole is much bigger than the amount that I'm displacing it. Okay? So anyone confused about the warm-up, let's just look at a picture just so you're clear. So I'm at some r equals B. I'm just going to, after some amount of time, I decide to move over to a new position, r equals B plus T, and I'm going to hold it there forever. We'll just want to know, what is the radiation field produced by this? Okay. And to analyze this, in particular, to analyze the radiation on the horizon, it's very useful to look at Maxwell's equations on the horizon. And Maxwell's equations take a very simple form where you can interpret the left-hand side and right-hand side in a kind of nice way. So the left-hand side corresponds to the radial component of the electric field on the horizon. And you should think of that, and you'll see why in a second, as basically registering the Coulomb field, Coulombic information on the horizon. Okay. And the radiation is this angular component, basically the component tangent to the horizon along the black hole. And this is, when you excite this corresponds to radiation propagating into the horizon. And this D here is the covariant derivative on the sphere. Okay. Okay, so for a static test charge, or some body located at some r equals B, or any position outside the black hole, the electromagnetic radiation, for that static test charge, it's absolutely zero, and therefore there's no radiation into the black hole. This angular component vanishes. But And, as you might have just guessed, the radial component basically goes like, the charge over the distance from the horizon squared. So this is the formula you would have probably guessed anyway. I'm just telling you it's true. So a static charge does not radiate into the black hole or even off to null infinity. And its radial component it registers just depends on its distance from the horizon. Okay. So now we want to do this process that I mentioned before, where I take a particle that's initially has that configuration on the horizon. I'm going to slowly displace it to a new position. Okay. And so again, since I'm doing this slow displacement, I can make the magnitude of this electric field that I'm generating on the horizon by moving this, by slowly displacing, as small as I want. Okay. So maybe at this stage, you should not be so worried. How could a black hole acquire any which path information? However, there's one constraint, which is that since the change in the radial component from early to late times cannot be zero, I have the following constraint, that the total integral of the electric field throughout this process cannot be zero. It actually is proportional to the change in the radial component. So even though the electric field is very small, its total integral along the horizon can be as big as I like, depending on what I'm doing outside. Okay? So this is going to be a problem. And you should think of it another way, which is in terms of the vector potential on the horizon, where the electric field in terms of the vector potential is just given by the time derivative of the vector potential. This implies, so if the integral of the electric field is non-zero, if I plug in this time derivative of the vector potential, I'm going to get that the vector potential must suffer a permanent change between early and late times. So the change in the vector potential is a gauge invariant statement, right? So the value at any one time is not gauge invariant, but the difference of the vector potential is gauge invariant. And I'm saying that it must suffer a permanent change due to this displacement. Okay? And we're going to quantize relative to the vector potentials. This is very important for later in this talk. Okay, so here's another picture. So I have this vector potential. I have a particle. I mean, I can set the value of the vector potential to be whatever I want at early times. I'm just going to set it to be, I guess, 0 in this particular case. I have a particle, located at some distance b, and with this value of the vector potential. But what am I doing when I move this particle to its new position? This registers as a change on the horizon of the vector potential. That corresponds to this step-like behavior in the vector potential. And the magnitude of the change in the vector potential is just given by the change in the radial component that I'm changing on the horizon. So the horizon, in some sense, is registering this change, even though I can do this as slowly as I like. Okay? Okay, so how could this lead to any big problems? It's just a very simple thing. But now, this has a huge effect on the number of photons emitted into the black hole. Okay, so let's compute the number of horizon photons. And in order to do that, we need to quantize the electromagnetic field on the horizon of the black hole. Okay? And so in order to tell you the number of photons, I need to choose a vacuum state. And this is where the gravitational collapse is important. There's lots of different vacuum. If you've studied quantum field theory in black hole spacetimes, you know that there's a lot of different vacuum states, but there's only one that arises from gravitational collapse. This is what's called the Unruh vacuum. Unfortunately, well, one technical point that turns out to not be important for what I'll say, but I should mention, the Unruh vacuum is defined in terms of initial data on this past horizon here. And we want to quantize on the future horizon, because that's where all the data, I mean, it's very difficult to tell you what is going on the future horizon, but in terms of the Unruh vacuum in general. But at low frequencies, which is the regime that I'm in timescales much less than m of the black hole, the Unruh vacuum actually is equivalent to the Hartle-Hawking vacuum. So what I'll be talking about now is the Hartle-Hawking vacuum calculation, but the answer for the number of photons emitted in this process is equivalent to if I was using the Unruh vacuum. This is just a technical point for those of you who know the difference between the two. But the statement is that I can use this Hartle-Hawking vacuum because they just agree at low frequencies with the Unruh vacuum. Okay, so that's just a technical point, and the Hilbert space over this vacuum is the space of positive frequency solutions on the horizon with this finite norm. So what is this norm? Well, it's not important for you to remember all the details of this norm. All you have to remember is that it depends on the Fourier transform of the vector potential. It has this factor of omega in it. So this frequencies, it's an integral over positive frequencies, and then you integrate over the sphere. Okay, so that's all. And the reason why that's very nice is because for any classical vector potential, right, for these coherent states, the expected number of photons is actually just equivalent to the norm of this classical solution. Okay, so I just need to, if I want to know how many photons is emitted in this process, I just have to plug my classical solution on the horizon into this norm. Okay. Okay, so then hopefully you can now see the problem. If the vector potential suffers a permanent displacement between early and late times, then the Fourier transform must diverge like 1 over the frequency. This is the Fourier transform of a step function, basically, at very low frequencies. Okay, so it has to diverge like 1 over omega, and the expected number of photons is logarithmically divergent at low frequencies. So there's an infinite number of photons emitted in this process. Yes?
If you keep the beginning and the end state.
Yes. We'll do the finite time in a second. Okay, so what have we just learned? It's not exactly relevant because of the question that, well, we'll do the case relevant to Alice's experiment in a second, but just displacing a charge, you have a charge outside of a black hole, and you displace it to a new position, and you keep it there forever. You can displace it however you like. I did it slowly, but you can displace it very quickly if you want. In either way, it's going to result in an infinite number of soft horizon photons, soft meaning very low frequency photons emitted into the black hole. Okay. So now we don't want to consider, as was just mentioned, we don't want to consider the case where we displace the particle over, for a finite time, for an infinite time at this new position. We want to bring it back at some point to do an experiment, which we will do in a second. So if it is then displaced back after a time t, the number of photons, which we'll calculate, is finite, but can be very large for large t. Okay, so how should you think about this? Well, Alice's particle is originally at this old position. She displaces it to this new position. She holds it there for some amount of time, capital T, which corresponds to some amount of affine time on the horizon. It holds it there for some time and then brings it back down. And the number of photons will be logarithmically divergent in affine time, which means it's going to be linearly divergent in the proper time of Alice's experiment. And I just put the numbers in for Adam Burrows, who I guess is left at this point. So it's linearly divergent in the time in which I perform this experiment. Okay, so now we can fully analyze Alice's experiment, but let's consider, just to make it so I can match it to what I was doing before, let's consider the specific case where Alice has 2 branches of the wave function, but she keeps one stationary forever. She never displaces it. And the other one goes along this displaced trajectory, held for some amount of time, and then displaced back. Okay? So for simplicity, we're going to consider this case. Of course, the one that it never gets displaced never radiates, or radiates negligibly, to the degree of error that Alice can maintain this, her particle at that position, radiates absolutely negligibly, and the radiation out to Scry for both, we're going to assume that Alice does both protocols absolutely slowly as you want, so that both the radiation out to Scry is 0, or nearly as negligible as you want. Know which path information is radiated out to Scry. But the second component of Alice's wave function, it's well, so the second component, which is the one that, doesn't go on this displaced trajectory, emits no radiation. The first component is going to emit radiation into the black hole, as I just described, and it's going to emit an expected number of photons that's linearly growing in the time that you've made this superposition. Okay? So the decoherence is given by the following formula, as hopefully you remember from before, but now you should really think of this as decoherence due to the black hole. So I'm putting a BH on it because there's no other thing acquiring which path information anywhere else in the spacetime. And again, it's given by this formula. And again, if Alice emits an order 1 number of photons into photons in this case, into the black hole, Alice's particle will be completely decohered. Okay. So I guess I'm going to be pretty early. So in general, Alice's charge, so now we can estimate. So Alice, what she's doing is she's creating a spatial superposition, and she's going to hold it there for some amount of time. After the black hole it's emitting radiation over that amount of time into the black hole at a constant rate, even though it's emitting nothing out to sky. And therefore, the black hole is acquiring which path information on the superposition. And after a certain amount of time, she's going to have emitted an order 1 number of entangling photons and be completely decohered. She can then check it if she wants, but she can also hand it to I guess the next graduate student or the next one or whatever. It doesn't matter. It's decohered at this time. And what is this time? Well, it's really slow, so you don't need to worry about it for current laboratory experiments. So for example, if what is this? I guess this is if the sun was a black hole and we were doing this experiment on the Earth and we had an electron superposed over a meter, it's very slow. It's 10 to the 43 years in this particular case. However, if you do this experiment near the ISCO of the black hole, it's 5 minutes. So it's highly dependent on how far away you are from the black hole. And so don't start writing proposals for this. Today I'll comment, I think, on what the significance of all of this is in a second. But okay, and so let me also mention the gravitational case. So at the level of linearized quantum gravity, you can just run this exact same story over again. Now for massive bodies, there's an analog of every step of this calculation, just with an extra index, basically. So the analog of the electric field, which is this affine time component of the field strength, is the perturbed electric Weyl tensor, which is the affine time components of this Weyl tensor. The horizon radiation is given by the components of the Weyl tensor tangent to the horizon, and the Coulombic data is determined by the radial components of this Weyl tensor. You can derive an exactly similar formula for the relationship between horizon radiation and the sources, that the Coulombic data registered on the horizon, and this radiation data is related to the metric, the perturbed metric, by 2 derivatives now. But note we have 2 derivatives here. The story is exactly the same. If you have changes in the metric on the horizon, that's due to changes in the radial component of this field, which is determined by the Coulombic data outside. So displacing a massive body for a time t outside a black hole gives rise to a number of gravitons proportional to the time you displaced it in the exact same way as before. Okay, so now this is totally generic. Any creation of any quantum superposition outside a black hole will just start to decohere at a fundamental rate. And this particular case, again, it's way slower. So don't get too excited about that number because you got to read those things. So a similar analysis basically shows the exact same story. You create a quantum superposition outside the black hole. In this crazy example, you have an Earth superposed, its center of mass superposed over its own radius. The sun is again a black hole, and it decoheres in about 10 microseconds. Well, I think I have a comment here. Oh yeah, it would not be easy to put the Earth in such a quantum superposition. Okay, so let me conclude, I guess, 15 minutes early. So I guess there's lots of time for questions. And maybe I'll just go slowly through this last slide. So let me just first say what was just done, and then we can talk about what I think, well, the other things that we'll be writing about soon. So if one creates any quantum superposition outside of a black hole, the long-range fields of that superposition register on the horizon of the black hole, and the black hole inflicts a fundamental rate of decoherence, just dependent on how big the superposition is and how far away you are from the black hole. And it results in particular a constant rate of production of entangling photons or gravitons into the black hole. And after a certain amount of time, any superposition is completely decohered, and eventually a black hole will decohere any quantum superposition. Okay, one thing I should note, which I'd be happy to comment on a bit more, is this is really due to the presence of a horizon. If Alice performs her experiment outside of a star of the same mass, so the local geometry is the same, she can ensure that she emits no radiation out to null infinity if she does this process extremely slowly. And she can emit, and there's no radiation associated to the, when she maintains, a static superposition for some amount of time. Go ahead.
Is that because she slightly changes the star and changes?
So she will slightly change the star, and so there is some, but the question is, in order to determine which path information these are all the star is made up of a lot of bound objects or whatever, and you would want to you're not going to be able to displace the star very much by, yeah, what?
There's a little effect on the star.
There's a little effect on the star. It's not nearly like this. I mean, for example, you just do the electromagnetic case in just a neutral star, then there's absolutely no effect at all. So it's very dependent on the composition of the star, and it's not anything like this effect where you're just radiating a constant rate due to the creation of the superposition outside the black hole. Does this make sense, or maybe I'm misinterpreting your question?
Yeah, I think I'm trying to just figure out the difference between star and black hole.
Yeah, so the difference is basically in the star case, you would want you want basically the which path information to be registered in the star somehow. So it's certainly true, it gets displaced a little bit, like a very minute amount. But if it's all bound up, it's there's that displacement is basically negligible. Whereas opposed to in the black hole case, it has nothing to do with any displacement or tidal deformability of the black hole. It has everything to do with just the fact that there's a horizon there. So that's the statement, or that's the way I would phrase it.
Can I ask you a question?
Sure.
So in the middle of your talk, you approximated the outlook vacuum by the
Hard-Hawking, at least at low frequency.
Yeah, and I'm wondering if there's a difference between the result, your result in the black hole background and the result in the ring drive background.
Yeah. So that's
yeah, I'm wondering if there is if the black hole plays its essential role in the coherence.
There is an effect in flat space-time if you're a Rindler observer, but so there's a couple of different stories here. One is constant uniform acceleration is not enough to achieve this effect. So for example, in the star case, Alice's lab is uniformly accelerating outside a black hole, but there's absolutely no analog of this effect. So it's not uniform acceleration. It's the presence of a killing horizon. That's the key ingredient. So if you're uniformly accelerating in flat space-time, you have a Rindler horizon. And then, well, in here, I mean, we generalize the statement to show that all killing horizons decohere quantum superposition. So if you basically create a quantum superposition in the presence of a killing horizon, it inflicts this fundamental rate of decoherence. So in the cosmological horizon, that's another example, it does the same thing.
So which part of your analysis
Needs the killing.
Existence.
Yeah. Well, it shows up a few places. One is like the killing horizon usually comes as a piece of the a late time Cauchy surface, and so the statement that this piece of the Cauchy surface is what's decohering you is a statement that you've collected all of the radiation everywhere else. That's one particular point. One more key point is this relation, which basically the killing horizon gives a clean separation between Coulombic data outside the horizon and radiation into the horizon. This is generically for an arbitrary null surface. This equation does not hold. Okay. Any other questions? Yeah.
It's very hard to understand why this keeps holding the time and time. Then it's in some sense longer wavelength of these photons that are trying to be registered or measured by the black hole. Shouldn't there be a low frequency cutoff to that? If I could say about like once the wavelength of these photons is much larger than that of the black hole.
Yeah, so that's a really good question. So that intuition, I think, comes from like shining source-free radiation onto a black hole and asking how much of that radiation gets absorbed. But if you look at this expression here, what's really driving the what I'm basically claiming is that black holes are much more efficient at absorbing low frequency radiation when it's driven by sources in their exterior. That's what this equation says. If you slowly vary a massive body outside of a black hole, the black hole is very efficient at absorbing that radiation. I don't have a better answer than that right now, but that's what this equation says. Yeah.
So I'm reminded of thinking about Schrodinger's cat in Feynman's day.
Sure.
We used to say that a cat is a macroscopic object. Its energy level spectrum is fantastically dense. If I have two portions of a cat, one quick and one dead, the difference in gravitational potential is enough to drive the energy level differently in the quick and the dead cat, to the point that the quick and dead cat plus the box plus the explosion, it becomes a mixed state. Either to an excellent approximation, it's either quick or a dead cat. You have invoked Alice, who is a macroscopic object, and is it in principle possible to have Alice do the experiment of waiting on whether this particle is there or is not in a pure state without affecting the particle?
Yeah.
Always going to have to observe it.
She will have to observe it. That's certainly true. But are you saying so? What?
You need the black hole.
Well, no. So I'm saying that even in flat space time, like she will have to observe by looking at by measuring the spin, for example, in the x direction, and to measure quantum coherence of her system. Is that what you mean, or?
Yes. But how does she avoid affecting the particle in this time?
Oh, so this is the statement of creating the quantum superposition in the first place.
And then standing in front of that is independent.
Yeah.
Not to affect the state vector of the solution.
Yeah. So it is a difficult experiment to achieve. You're asking whether in principle it could be done. Yeah. Yeah. So I would say, well, people have done this in the lab. That's one experimental evidence where people have created these spatial superpositions. Yeah. And kept them quantum coherent, not for the timescales that I'm asking for in this talk. So I'm saying that I definitely, I'm assuming that Alice is a good enough experimentalist that she can, achieve a spatial superposition, and in the absence of the black hole, be able to maintain quantum coherence. So that, that's certainly an assumption of all of this. But the statement is that that's at least experimentally true that they're able to do that. Yes.
Can I ask a timescale question? So, if I would consider like the timescale at which you can measure order one decoherence, and I would compare that to the time scale of Hawking radiation,
Yeah,
radiating away half the black hole.
right.
And do you have a comparison?
Yeah. Like even for the electron case, like this would be like something like for the massive star, for a star of solar mass is like 10 to the 60 years roughly is the Hawking evaporation timescale. Yeah, so it's like m cubed. So this is all much less than that. Like
But there must be a threshold in mass of black hole.
yeah. If you
for
do,
which,
yeah.
for which the two times cross.
Well, mass of the black hole and how you have to fix a couple of things because the charge and the distance away from the horizon
Yeah.
and things like that. There are cases in which it would these effects are competing, but there are huge ranges of cases where there aren't, and I like to stay away from the cases when they are. Yeah.
Two questions. So it seems that an experiment to describe, and this is immersed in the realm of Hawking.
Yeah, it's a good question. Yeah.
You have a back of the envelope.
Yeah. So
Smaller.
it's way smaller. So the statement is that for a solar mass black hole, so the question is basically the black hole, and I was going to talk about this, but I thought I wouldn't have enough time, but clearly not. For a solar mass black hole, for example, the Hawking temperature far away from the black hole, far away being more than like a few m's away from the black hole, is absolutely weak, very low, and therefore the collisions of the Hawking quanta with this superposition is absolutely negligible. Like it's basically based on the size of the separation of the superposition. No, you can actually, yeah. So the time scales. Yeah.
So very nicely, the number of photons that Hawking photon that absorbed by the sun, and
Yeah.
the one value is like 1 square.
Well, it depends on the size of the superposition because it's not just absorbing, but you have to absorb and it has to hit one branch of the superposition differently than the other. So it's dependent on the size of the superposition only. Like it's also dependent on whatever, like the dilution of the. Yes, yeah. Yes, it's a different dependence than D, so it's a different effect, and you can estimate the time scale due to, I guess in this paper I can write down the formulas for you, but it's a different effect, and you can estimate the time scale due to decoherence from Hawking quanta. It's very big if you're extremely close, like about 3m or less away from the black hole. You're extremely close. This effect dominates, but if you're far enough away, more than a few m away, definitely if you're at 6m, it's completely negligible. Okay, I guess I should conclude now. Okay, so as I mentioned, and as a lot of people I think probably already know, this effect is absolutely not important for any current practical experiments. But I mean, in the spirit of Feynman, it's really maybe teaching us something of fundamental importance for our understanding of the nature of black holes and, as we'll point out shortly, horizons in general in a quantum theory of gravity. Like there's some intrinsic way in which these horizons, are obtaining which path information on quantum superpositions that that really comes, maybe is teaching us something about the fundamental aspects or properties of quantum gravity in general. Okay, so let me end there, and then I'll take more questions.
So I think that in your direction, assume you are displacing the particle in the radial direction.
Yeah.
What happens when you are separating them in the angular direction?
You can separate in the angular direction. It's just like basically the question is how much does this Coulombic data change in the horizon? It's much less when you separate it in angular. So I just gave the optimal one, but optimal in terms of, well, actually for Alice it'd be optimal to do the angular one, I guess. But in either way,
But still there's the fact that
yeah, exactly. There is an effect. Basically, if you make any superposition at all outside the black hole, it's just an effect. It's just estimating the timescales depends on how you've made the superposition. So I should say, like, there's also like you could just do this for a full wave packet, and do this calculation too. This should I guess, also come out fairly shortly. And you can see that the wave function of the particle is becoming incoherent over its own, wave packet, and dispersing, or sorry, getting very spiky basically, because you're getting basically decoherence in the position basis of the wave function over time. And you get this like very spiky wave function after some time, just due to the presence of the black hole. Like that's another example.
And another question, what is the time scale of this superposition for the cosmological crisis?
Why don't I talk to you after? Because I don't remember off the top of my head. I could maybe guess. It's slow. I think I think they're all slow. There's some interesting cases I think that one could consider in the cosmological case, but maybe I won't say it since this is all being recorded and I don't want to say something wrong.
No further questions. Let's thank God again.